In this episode, we're going to look at the transient period of an RL circuit and see what happens to the resistor and the inductor as the current is changing over time. So let's go ahead and get started. So we're going to start our discussion with a very basic RL circuit, and we call it RL because it obviously has a resistor and an inductor in it. Okay, and so again, we have a switch in the circuit because we're concerned about when that switch is thrown as being time equals 0. It doesn't necessarily have to be time equals 0, but for our intents and purposes, that's what we're going to use it for. So at time equals 0, the contacts make a connection, and we have all of our initial values. Okay, so we've got a 10 volt source here, we've got a 1k ohm resistor, and we've got an inductor of 1 millihenry. Okay, so the period of time that we're talking about is the transient period. So this is what happens before the circuit gets to steady state. With RC circuits, we looked at the transient period and saw that initially all the voltage is on the resistor and none of it's on the capacitor because it hasn't had time to accumulate charge on the negative plate. So it takes 5 time constants for the voltage essentially to move from the resistor over to the inductor. Okay, so the opposite is going to happen with an RL circuit. We're going to have all the voltage initially on the inductor, and then essentially it'll be released over to the, it's not really released, but this will reach a steady state value for current, and that happens at 5 time constants, just like with the voltage regulating itself on the capacitor. So after 5 time constants, all the voltage is off of this, it becomes a short, and all the voltage is on the resistor, and we're operating at maximum current. Okay, so in other words, it looks just like if you were to just take 10 volts divided by 1K. So there's a 10 milliamp current that's running through this circuit at steady state, because this will essentially look like a short. So again, the transient period is the change that occurs after some event, like a switch opening or closing, or a voltage source increasing or decreasing, or something like that. So initially here, without the switch thrown, we have no voltage on the inductor, we have no voltage on the resistor, and since we have no voltage on the resistor, we have no current. So this is the moment that the contacts make a connection. So now, the inductor voltage is it has all the voltage of the 10 volt source because it was at 0 milliamps and it wants to remain at 0 milliamps. So it grabs all the voltage from the resistor. So initially we are at 0. However, over time, that's going to increase up to whatever that 10 milliamp value is for this circuit. But initially, we're still at 0 milliamps because the inductor cannot instantaneously change the current. Okay, resistors can. If this was just a DC circuit, we know that there's an instantaneous change on the voltage on the resistor if the voltage of the source changes or if something else changes. But for an inductor, it cannot change current instantaneously, so it has to change over a matter of 5 time constants. So this is t equals 0. Now let's see what happens when we get to steady state. So no voltage on the inductor, all the voltage is on the resistor, and we are operating at maximum current at this 10 milliamps. So it's like the inductor doesn't even really exist. Okay, now this is a little bit different from the RC circuit as well. If you were to charge up a capacitor to the voltage on the source after 5 time constants at steady state, and you were to open the switch, that capacitor retains its electric field, its electric potential. When an inductor stores its electromagnetic field and you open the switch, it immediately goes to ground. Okay, so it does not retain its, that would be like a flux capacitor, which is a figment of the creators of Back to the Future's imagination, right? So it'd be great if we could do that, but we can't. We can store it in an inductor, but as soon as you remove power from the circuit, it's gone. So it says a voltage spike appears across the switch as it is open. So once we are in this steady state condition here and we're operating at a certain current, if you open that switch, remember what happens with the magnetic field if you are trying to decrease the current, because that's what you're doing. You're going from one current and you're trying to decrease it, and so it will collapse on itself. Okay. So you might remember this from a previous discussion on inductors, but Lenz's law says that if you try to decrease the current, okay, the magnetic field is going to collapse on itself, and it's going to try to use that energy to maintain the current that it's at. Okay, so in our situation, we are currently at a steady state current of 10 milliamps, and if we try to open that switch, when that magnetic field collapses, you're going to see a voltage spike across the terminals here. Now, sometimes it's not very severe. Sometimes it can be pretty dramatic if there's a lot of resistance and inductance in the circuit. Okay, and there are videos on YouTube that will explain this, and I'll put a link to those in the comments of this video. Okay, and there's a video from MIT that shows what they call a back EMF. You get this electromotive force that exists between the terminals because the inductor is trying to maintain that 10 milliamp current and collapses the magnetic field to use that energy to get it to continue to operate. Okay. If you can control it, you can actually. That's how automobile ignitions work, by switching a current through an inductor, and with the intention of creating a spark to make it, to start the internal combustion of an engine. So if you want to prevent that from happening, you can put in what's called a spike suppression diode. And so you can see here, we've got one that's in parallel with the inductor. And so instead of when this thing tries to collapse on itself and the energy has to go somewhere, instead of it spiking through here, it gives it an alternate path to sort of spin itself out. So this will protect the coil from being over voltage too quickly and burn it up. So we do have a calculation for the tau for an RL time constant, and that's just L over R, where with RC time constants, it was just resistance times capacitance. Here, we take the inductance value and divide it by the resistance, and that will give us time. It will give us seconds, okay? So it says for the preceding RL circuit, the time constant is 1 millihenry over 1 kiloohm, which would give you 1 microsecond. So it takes 5 microseconds for that previous circuit to get to steady state, and that was this one right here, okay, where we have the 1K and the 1 milli. Okay, so again, the calculation, L over R for tau. So it says the inductor opposes instantaneous change in circuit current. Again, this is the V equals L didt, and you will hear that repeated over and over if you continue on and do higher level circuits courses. L didt and C dVdt. Those are the two that we typically use to describe what's happening in the circuit and describes the actual opposition. So with capacitors, it's C dVdt. So if you have a changing voltage on the capacitor, okay, you have a current. If the voltage on the capacitor is no longer changing, you have no current, because it's at steady state. So by the same token, just an explanation of this equation again, if you have a changing current, if you're at steady state current, this didt term becomes 0 and you have no induced voltage on the inductor. However, if you do have a changing current, the inductor is going to pull some of that voltage over, and it's going to take 5 time constants to release it back to the resistance. But if it's a constantly changing current, like with an AC, it may never get back to steady state. So it could be constantly inducing a voltage on its terminals. So once again, the same principles of growth and decay apply to these functions. And so a time constant is the time it takes for the current to increase or decrease by 63%. And we went over that in the RC transient discussion. So it says 5 time constants for the current to reach steady state. So that is all essentially from before. So just to take a look at the exponential rise and decay again, here's the exponential growth curve, here's the exponential decay curve, and both of these are referenced to an amplitude of 1 and 1 in both cases. Okay, so the voltage here, the reason why there's no Vs out in front is because we're assuming that this is charging to 1 or going from 1, or I'm sorry, the other way around. If we're going from 1 and charging to 0, or if we're going from 0 and charging up to 1. So there's an implied out in front here, multiplier out in front here. Okay, so here you can see the 63% is actually like 63.21%, but for all intents and purposes, we just say 63%. And even when we get to 5 time constants, we're only at 99.3%. The reason why we say that is steady state, because everything after that is 99%, and it never gets to 100%. So once we've crossed that threshold, we assume that we are in a steady state condition, because as you know, with both growth and decay functions, you never actually decay to the number you're decaying to, or grow to the actual number. You get very, very close. In fact, if you take it out to infinity, at t equals infinity, you will get infinitely close, but never actually touch. Okay? Same thing with, decaying down to 0. You will get infinitely close to 0, but never actually touch, or whatever the asymptote is. We know that with inductors, there's inherent voltage drop, so, technically the voltage on the inductor is not going to decay to 0. It's going to decay down to whatever inherent voltage drop there is, because the inductor is made of a conductive material that has an inherent resistance. Okay? All right. So let's go ahead and take a quick look at what we're going to apply for the circuits in our case. And we are going to apply in the lab a square wave. Okay, and so I kind of went over this in the RC discussion, but with a square wave here, it's 4 volts peak to peak. So we go 4 volts, we rest at a DC voltage, and then we come back to 0. In this case, we're doing from 0 to 4, okay, instead of just 2 to 2, like you see here. Okay, so this is what we call an offset signal. So that way that instead of going, this is without an offset, it would go from -2 to 2. So you still have a 4 volt peak to peak signal. However, you do have negative voltage on the source. Whereas with this one, with the offset, you've put in an extra 2 volts DC that it rides on, and so now it looks like the source is 0 to 4 volts and is an actual like a square wave generator. Okay, so that means that instead of the voltage on the resistor looking like the voltage on the capacitor, right? Because it's just growth and decay, we go from -2 up to 2. But if we have an offset, we go from 0 up to 4. Okay? And so what happens with the voltage on the inductor? Well, without the offset, again, because this is a 4 volt peak to peak, we're going to go 4 volts in this direction. So that's a 4 volt increase, and we decay back to 0. And then from this position here, when you go from +2 to -2, that is a -4 volt increase. Remember, the voltage on the inductor, that's where it gets induced and pulls it, right? And then it releases it back, and then it pulls it and releases it back. So in both cases, whether you have an offset or not, only affects the voltage on the resistor, because as you can see, with an offset, we're still just going 4 volts. So the voltage on the inductor is not affected by the DC offset. All right, so let's go ahead and go to the board and look at some circuits, and we will work some of them out. Okay? Okay, so here you can see the equations that we're going to use for the RL this time. And so everything looks kind of backwards from what it was before with the RC circuit. So for an RL circuit where we have a resistance and an inductance, the voltage on the inductor is a decay, and so it's the voltage to the source times the decay portion, e to the -t over tau. Okay. For the voltage on the resistor, we have the voltage source times 1 minus e to the -t over tau. And remember, this portion right here, this is a growth function. This portion right here that's multiplied against is a decay function. So both the resistor, whatever the resistor does, the current is going to do as well, because they're always in phase with each other. So the voltage on the resistor, the voltage times the source times the growth part. The current at any point in time is I max times the growth portion, 1 minus e to the -t over tau. And I max, again, here is voltage over the total resistance. And tau is the L over R. Okay, and tau is, again, in seconds. Okay, so let's go ahead and we're going to take a look at an example here. So here we have an example where we've got a 9-volt source and a 1.2 k ohm resistor and a 10 millihenry inductor. Okay, so let's go ahead and find tau. It's the first thing we would do, just like with the RC circuit. This time it's L over R. So we've got 10 millihenry divided by 1.2K. So 10 E negative 3 divided by 1.2 E3. And I get 8.33 microseconds. Okay, and that's micro. Okay, so that means 5 time constants is roughly 41-ish microseconds. So let's take a look at t equals 10 micro, and let's take a look at t equals 30 microseconds. Okay. Again, so 5 tau is roughly, 5 times this is roughly, let's say 42 micro. Okay. So we're looking at just after 1 time constant and before we get to 5 tau. Okay. 5 tau. All right. So the voltage on the inductor at so these are all 10 microseconds. Okay, I'm not going to do the time. So we've got the voltage of the source 9 volts. Now remember, this one is a decay, so e to the negative 10 microseconds over the 8.33 microseconds. And I get 2.71 volts. Okay. Voltage on the resistor is going to be 9 times 1 minus e to the negative 10 microseconds over 8.33 microseconds. So I can modify my equation slightly here, add a couple of parentheses. I come up with 6.29, which is good because these two numbers should add up to 9 volts. Okay, so my I max in this case is 9 volts divided by 1.2K. That's my only resistance here. So 9 divided by 1.2, and I get 7.5 milliamps. So that means for I, at this point in time, 10 microseconds, we've got 7.5 milliamps times 1 minus e to the negative 10 micro over 8.33 micro. And I come up with 5.24 milliamps. Okay, so there's our 3. So the voltage on the L, the voltage on the R, and the current. We had 2.71 volts, 6.29 volts, and we were at 5.24 milliamps. Okay, now let's take a look at the next point in time. So this is going to be, the inductor is going to have very, very little at this point. We want to keep the max current here. So the voltage on the inductor at this point in time, so this is 30 microseconds. Okay. So the voltage on the inductor is still going to be 9 times e to now the negative 30 microseconds over 8.33 microseconds. And I come up with 246 millivolts. Okay, so again, it's not going to have very much because we're almost to 5 tau here. So now the voltage on the resistor is going to have the majority of this, right? So 9 times 1 minus e to the negative 30 micro over 8.33 micro. So again, I'm modifying my equation just slightly. Add a couple of parentheses. I come up with 8.75 volts. So 250 millivolts essentially plus 8.75 volts will give you the 9 volts. Okay, so the I in this case, so 7.5 milliamps times 1 minus e to the negative 30 micro over 8.33 micro. And we're at 7, we'll call it 7.30 milliamps. Okay, so we're almost to 7.5. Okay, so there you can see the difference. So early on, still after one time constant though, the voltage on the inductor was still at 2.71, the voltage on the resistor 6.29, and 5.2 milliamp current. And here, further in time, closer to this 5 tau, now you can see the majority of the voltage is on the resistor, almost none of it is on the inductor, and we're approaching max current. Okay, so let's go ahead and ratchet it up a little bit and add some more components. Okay, now in this case we've got 2 resistors and we've got 1 inductor. Okay, so let's see how that changes things. Really, the first thing that's going to change is tau, because this is L over R. But if you've got more than one inductor or more than one resistor, you have to find the total of each. So really you could look at this as sub T in each case. Okay, so the total here is 9 millihenries of inductance, and then you add these together, you get 4 kiloohms of resistance. Okay, so I'm going to take 9 milli divided by 4K. And I get 2.25 microseconds. So that puts us at like just after 10.25 at 5 tau. Okay, so let's look at point t equals, let's do t equals 1 micro, so quicker. And then let's look at t equals 9 microseconds, so before 5 tau. Okay. All right, well, let's go ahead and look at the voltage on the inductor first. And so the total voltage is 10. Again, this is a decay function, so it's e to the negative. In this case, t is 1 microsecond. So that's what we're looking at here, 1 microsecond. So 1 micro over 2.25 micro. So we're not very far into it at this point. Okay, so let's do this calculation. And I get 6.41. 6.41 volts. Okay. And then for the next one, for the resistor, so 10 times 1 minus that, 1 micro divided by 2.25 micro. Write this off to the side here. So again, now I'm just going to go change this equation to put the 1 minus in with a couple of extra parentheses. And 3.59. Which again is good because those two voltages add up to the total. And so in this case for our I max, again this is V over the resistance total. So we have total of 4K here, so that's going to be 10 volts divided by 4K, and that's 2.5 milliamps. Okay, so the I is going to be 2.5 milliamps times the growth, so negative 1 microsecond over 2.25 microseconds. So I just change out front. Instead of 10, I have 2.5 milli. And I get 897 microamps. Okay, so at 1 microsecond, I'm going to write these over here in a different color. How about red? So for 1 microsecond, we had VL, and we had VR, and we had I. And so this was 6.41, 1 volts. This was 3.59, 3.59 volts. And this one, 897 microamps. Okay, now let's look at the other point in time. Get rid of this. Need to keep the 2.5 max current here. All right, so now we're looking at 9 microseconds. So this is just before, again, this is just before 5 tau, steady state. So the voltage on the inductor is going to be 10 volts times, now this time, it's e to the negative 9 micro over the 2.25 micro. So that's 183 millivolts. So almost nothing. We waited even longer in this example to see what happened. So voltage of resistance, 10 times the growth, 1 minus e to the negative 9 micro over 2.25 micro. Let's see what that is. I'm going to write that one off to the side here too. Add in the 1 minus. And I get 9.82. Now, does that make sense? That looks like it. Okay, so about 0.18 millivolts plus 9.82 volts gives you 10. All right, now the current, still 2.5 milli, times the growth part, negative 9 micro over 2.25 micro. And there we get 2.45. So almost there. 2.45 milliamps. About to run out of ink on my marker here. Okay. So there we go. So you can see here, at just before, we had still gotten pretty far, right? There's a pretty big jump at the initial, growth part or the decay part, and then everything gets closer to the asymptote and slows down. So, even before that, we're at 6.4 here, 3.5 here, but then you go closer to 5 tau, we're all the way down to 183 millivolt and all the way up to 9.82 and operating at 2.45 milliamps, okay? So now let's do one where we add a couple of inductors. Okay, so in this case now we've got 2 resistors and 2 inductors, okay? So, same thing. Maybe I need now to up here do my total resistance to keep track of this. So 100 plus 200 is 300 ohms. My total inductance, these are in series, so I treat them like resistors in series and just add them together. And so my total there is 30 millihenries. That means my tau is LT over RT, which is 30 milli divided by 300. So let's see what we get. And we get 100 micro. That makes it easy. So half a millisecond, or 500 microseconds, will be at steady state. So let's look at t equals. Let's go really, really quick. How about 10 microseconds? And let's also look at t equals. Well, let's go ahead and look at 500. 500 micro. We'll look at 5 tau. So this is steady state. Okay? So the first one's going to be 10 microseconds. And I'm going to go ahead and find Imax now. Might as well. So I've got 20 volts divided by the total resistance, which we said was 300 ohms. So it's 2/3. And obviously 66.7 milliamps. Okay. So the voltage on the inductors, if you need to, say voltage of L sub T. Okay, and then you can do your voltage division from there. All right, but the total voltage on the inductors together is going to be 20 volts times, again, this is an exponential decay function, so e to the negative, in this case it's 10 micro over 100 micro. And there I get 18.1. So the majority of it's still on the inductor at this point. 18.1 volts. Okay. Voltage on the total resistance. So 20 times the growth, e to the negative 10 micro over 100 micro. So 1.90, as you would expect, because both of these have to add up to 20. And so now my I, I'm going to use this Imax, so 66.7 milliamps times 1 minus e to the negative 10 micro over 100 micro. And so there we get 6.35 milli. So not very much to start off with, considering it's going all the way up to almost 67 milliamps. Okay? So that's taking a picture at it really early on. Again, the time constant here is 100 microseconds. Okay, so let's get these transferred over here. So at 10 microseconds, the voltage on the inductor, resistor, and current. So we had 18.1 volts, and we had 1.90 volts. And we had 6.35 milliamps. Okay. Now we'll take a look at this 500, looking at steady state, or what we consider steady state. So, on a quiz or an exam, if I say at t equals infinity, or if I say t equals steady state, or if I say t equals 5 tau, I'm talking about the same period of time, okay? So this and this and this, for what we're doing, is all the same thing, okay? So I'm looking at 5 tau. Okay, so here's the thing. I could go ahead and say that at 500 microseconds, which is 5 tau, the voltage on the inductor is 0, the voltage on the resistor is 20 volts, and the current is 66.7 milliamps. And technically, I would be correct, okay? However, the equation, the exponential equation, again, it's approaching an asymptote. So if we want the actual value, we still have to plug it in and see what those values are, okay? If you do this on the quiz or the exam, though, I will not count it wrong. If I'm giving you a point in time that is 5 tau. So the voltage on the inductor 20. This is decay, so e to the negative 500 micro over 100 micro. So this should be 99.33% of 20. And I get 135 millivolts, which is trivial, right? In a system this big, or with 20 volts here. So the voltage on the resistor, 1 minus e to the negative 500 micro over 100 micro. $19.9 volts. And then I, 66.7 milliamps, that's the max. Again, the growth. And I get 66 rounded up to 66.3 milliamps. Okay. So again, this is these voltages are across both. So if I wanted to find out what each individual resistor is, I take this 19.9 volts and then I do a voltage distribution here. Okay, and I do the same thing for the inductors. Okay, I can do, this is 20 compared to 10. I still use them in the same way that I would use voltage division ratios. Okay, capacitors are the oddballs. So again, so here we've got, circle this. So initially, very, very early on, well before the first time constant, most of the voltage is on the resistor or on the inductor. Almost none of it's on the resistor. And we are at 6.35 milliamps of current. So we're not anywhere close to the max yet. However, at steady state, only 135 millivolts of voltage on the inductor, 19.9 volts on the resistor, and we are almost at steady state current. Well, we are at steady state current, 66.3 milliamps. Okay? All right. So that should do it for the RL transients. Thanks for watching.